Download this code from codegive.com, link in the description below. OK, let's dive into web cache deception, WCD, attacks. This is a serious and potentially dangerous vulnerability that can expose sensitive user information. We'll cover the theory, practical examples, and mitigation strategies. What is web cache deception? Web cache deception, WCD, is a web security vulnerability that exploits the way some web servers and content delivery networks, CDNs, interact with web caches. In essence, an attacker can trick a cache into storing private, user-specific content associated with a public URL. Then, anyone visiting that public URL, including the attacker, gains access to that cached, private data. Key concepts ***. Web caches Web caches, often implemented by CDNs like Cloudflare, Akamai, or Varnish, or by reverse proxies like nginx, Apache, store static or frequently accessed content, images, CSS, JavaScript, HTML pages, closer to the users. This reduces latency, bandwidth usage, and load on the origin server. Cache keys A cache key is a unique identifier used by the cache to determine if a request can be served from the cache or if it needs to be fetched from the origin server. Typically, the cache key includes the HTTP method, GET, POST, etc., the host header, and the request URI, the path after the domain name. Variations in these elements result in different cache entries. Origin server The origin server is the real web server that hosts the application. It's where the application logic resides and where data is stored. Static versus dynamic content Static content remains the same for all users, example a company logo. Dynamic content is personalized and varies based on the user, example a user's profile page, bank account details. Cache poisoning Cache poisoning is a broader category of attacks where an attacker injects malicious or unexpected content into a cache, affecting users who later access that cached content. WCD is a type of cache poisoning. How it works 1. The setup The web application has some flaw in how it handles requests, particularly in the way it determines whether a resource should be served from the cache or generated dynamically. A common flaw is a failure to properly distinguish between static and dynamic content based on the requested URL. 2. The attack An attacker crafts a malicious URL that appears to request a static asset, example /static/image.jpg, but is actually processed by the server in a way that includes the user's private data. This often involves using path traversal or other URL manipulation techniques. 3. Cache storage The attacker sends this malicious URL to the server through the CDN or cache. Because of the URL's apparent static nature, the CDN/cache stores the response to this URL, including the user's personalized data. 4. Exploitation The attacker, or other users, now access the crafted URL again. The CDN/cache serves the previously cached response, which contains the private data of the user who initially triggered the cache. The attacker has effectively gained access to someone else's sensitive information. 2. Identifying the vulnerability. Finding a web cache deception vulnerability typically involves 1. Analyzing URL structures Look for patterns in how URLs are constructed. Pay attention to how the application handles path parameters, file extensions, and query strings. Identify URLs that look like they should serve static content but might be dynamically generated based on user data. 2. Testing with different user accounts Log in with two different accounts, A and B. Then, try to access a static resource with account A. Log out and log in with account B. Try to access the same static resource. If you see data from account A, it's a strong indication of a WCD vulnerability. 3. Checking cache headers *. Use your browser's developer tools, or curl URL, to inspect the HTTP response headers for clues about caching. Look for headers like cache control, expires, age, xcache, via, etc. These headers will tell you whether a resource is being cached and how long it's cached for. 4. Path traversal and URL manipulation *. Experiment with URL path traversal techniques, example /// or appending unusual file extensions, example /profile.php.css, to try to trick the server into serving dynamic content with a static URL. 5. Parameter confusion *. Try adding unnecessary parameters to static asset URLs. Sometimes servers will ignore these parameters and still return the requested file, but the cache will treat the URL with the extra parameters as a new entry. 3. Example scenarios and code illustrations. Let's consider some hypothetical scenarios and illustrate how WCD could be exploited. I'll use Python/Flask for simplicity in the server-side examples. Scenario 1, profile page with a static CSS file. Vulnerable application *. The application has a user profile page, /profile, and includes a CSS file that's supposedly static, /static/profile.css. However, the server-side code dynamically generates the CSS based on the user's settings, example color preferences. HTML templates, templates/profile.html and templates/index.html. Attack. 1. Alice logs in, or her username is set via the cookie. She visits /static/profile.css. The server dynamically generates CSS based on Alice's username and returns it with the correct content type. 2. The cdn/cache sees a request for /static/profile.css and caches Alice's generated CSS. 3. Bob logs in, or his username is set via the cookie. He visits /static/profile.css. 4. Instead of the server generating CSS for Bob, the cdn/cache serves the cached CSS that contains Alice's personalized styles. Bob's profile page now reflects Alice's color preferences. Proof of concept, using curl. 1. Alice sets her username, simulating login. Examine the response headers to note the set cookie header. 2. Alice requests the CSS, and the cache stores it. 3. Bob sets his username *. 4. Bob requests the CSS, and gets Alice's cached version. Examine the output. You'll likely see Alice's CSS content, even though Bob made the request. Scenario 2, path traversal leading to information disclosure. Vulnerable application *. The application allows users to download files using a URL like /download, file equals foo.pdf. It attempts to sanitize the input, but the sanitization is flawed. Attack. 1. The attacker crafts a URL like /download, file equals / etc. /password.css, or /download, file equals / upload sensitive.txt.css. The goal is to use path traversal to access a sensitive file on the server. The .css extension is added to make the URL look like it's requesting a static CSS file. 2. If the server's sanitization is weak, it might not properly prevent the path traversal. The server could end up reading the contents of /etc. /password or the sensitive text file. 3. The cdn/cache sees a request for a URL ending in .css and assumes it's a static file. It caches the response, which now contains the contents of the sensitive file. For the attacker, or anyone else, can now access /download, file equals // etc. /password.css and retrieve the cached contents of the file. Asterisk proof of concept asterisk. 1. Request the vulnerable URL asterisk. 2. Examine the output. If the path traversal works and the response is cached, you'll see the contents of sensitive.txt. Subsequent requests will retrieve the cached version. Scenario 3, Session ID in a static JavaScript file. Asterisk vulnerable application asterisk. The application generates a unique session ID for each user. This session ID is used for authentication and authorization. For performance reasons, the application tries to embed the session ID in a JavaScript file that's supposed to be static, /js/config.js. Asterisk HTML template profile.html. Asterisk attack asterisk. 1. Alice visits /js/config.js. The server generates a unique session ID for Alice and returns it in the JavaScript file. 2. The cdn/cache sees a request for /js/config.js and caches the response, including Alice's session ID. 3. Bob visits /js/config.js. The cdn/cache serves Alice's cached session ID to Bob. 4. Bob's browser now uses Alice's session ID. If the application uses the session ID for authentication, Bob might be able to impersonate Alice. Asterisk proof of concept asterisk. 1. Alice requests the JS file asterisk. 2. Note the session ID in the response. 3. Bob requests the JS file asterisk. 4. Bob will likely get the same session ID as Alice from the cache. 4. Mitigation strategies. Preventing web cache deception requires a multifaceted approach. 1. Properly configure caching asterisk. Asterisk cache only static content asterisk. Configure your web server and CDN to only cache truly static resources, images, CSS, JavaScript files that never change based on user input or authentication state. Asterisk avoid caching pages that require authentication asterisk. Do not cache HTML pages that require authentication or that display user-specific data. Use the cache control, private header for these pages. This header tells caches that the resource is only intended for the user's browser and should not be stored in shared caches. Asterisk use the cache control, no cache and cache control, no store headers asterisk. These headers tell caches to not cache the resource at all. No cache allows the cache to revalidate the resource with the origin server, while no store prohibits any caching. Asterisk vary header asterisk. The vary header is crucial. It tells the cache that the content of a resource can vary based on the value of certain request headers. For example, vary cookie tells the cache that the response can be different based on the cookies sent in the request. If you're generating dynamic content based on cookies, set the vary cookie header. Vary except encoding is also common for handling zip compression. 2. Strong input validation and sanitization asterisk. Asterisk prevent path traversal asterisk. Implement robust input validation to prevent path traversal attacks. Use allow lists of permitted characters and file extensions. Avoid using user-supplied input directly in file paths. Asterisk carefully sanitize URLs asterisk. Be cautious about how you process and interpret URLs. Ensure that any URL manipulation logic is secure and doesn't allow attackers to bypass intended restrictions. 3. Session management asterisk. Asterisk never embed session IDs in static files asterisk. This is a major red flag. Session IDs should be stored securely, example in cookies with the HTTP only and secure flags set, or in local storage encrypted if necessary, and managed appropriately by the server. Use proper session handling mechanisms. Utilize secure session management frameworks that provide protection against session fixation, session hijacking, and other session-related attacks. Regenerate session IDs. Regenerate session IDs after significant events like login or privilege escalation. For code reviews and security audits. Regular code reviews. Have your code reviewed by security-conscious developers to identify potential vulnerabilities. Penetration testing. Conduct regular penetration tests to simulate real-world attacks and uncover weaknesses in your application. 5. Web Application Firewall, WAF. Deploy a WAF. A WAF can help to detect and block malicious requests, including those that attempt to exploit WCD vulnerabilities. Configure your WAF with rules to prevent path traversal, invalid file extensions, and other suspicious URL patterns. Revised code examples, with mitigation. Let's revisit the earlier code examples and apply some mitigations. Scenario 1, Mitigation Profile Page CSS. Changes renamed root instead of /static/profile.css, the root is now /profile_style. This makes it clear that the resource is dynamically generated and not a true static asset. Cache control headers. The cache control header is set to private, no cache, no store, must revalidate. This tells caches that the CSS should not be cached. It is private to the user's browser. It must revalidate with the origin server if it were to cache it, but the no store prevents that. Link the CSS dynamically in the HTML*. Scenario 2, Mitigation Path Traversal. Changes allowed file extensions. Implemented an allowed_file function and allowed_extensions set to restrict the types of files that can be downloaded. Robust path traversal prevention. os.path.obspath converts the file path to an absolute path. File path.startsWith checks that the absolute path starts with the upload_folder. This ensures that the requested file is actually within the intended directory and prevents traversal to outside directories. Scenario 3, Mitigation Session ID in JavaScript. HTML template, template/profile.html. Changes. Server-side sessions. Using Flask session to manage sessions server-side, using cookies. No session ID in JavaScript. The /js/config.js root now does nothing. The session_ID is now retrieved from the server-side session. Session storage, storing the session_ID in the session object rather than returning it as JavaScript to the client, mitigating the web cache deception attack. Conclusion. Web cache deception is a subtle but potentially devastating vulnerability. By understanding how caches work and by following secure coding practices, you can significantly reduce your application's risk of being exploited. Remember to always validate user input, properly configure caching, and regularly review your code for security flaws. Security is an ongoing process, not a one-time fix. Keep learning and adapting your defenses as new threats emerge.